In this chapter, we'll look at the chemistry of carbon composites, their composition and structure, and an interesting and unexpected property. Few people for carbon will shop for rims at $1,000 a pop. It'll find potential and growth exponential when prices eventually drop. Carbon composites have their own vocabulary, and these are some of the terms you'll become familiar with in this chapter. First is a little detour into what is, I'm sure, your favorite course, organic chemistry. This is a molecule of acrolein, and this is a molecule of acrylonitrile. The difference is that the aldehyde group in acrolein is replaced with a nitrile group in acrylonitrile. Acrylonitrile is easily polymerized. For completeness, I'm putting an unshared pair of electrons on nitrogen, and this is the repeating unit in acrylonitrile, and there can be as many of these repeating units as the polymer is long. So when the polymer builds up, it looks like this: one unit, and then another, and so on. So this is the structure of polyacrylonitrile, PAN, and that's where the abbreviation PAN comes from. And this is the precursor for most carbon fiber products. The precursor goes through several stages, the first of which is called carbonization, and that forms an intermediate, and then graphitization to form the carbon fiber, which is going to be graphite or graphite-like, and both of these processes are done at high temperature and require quite a bit of heat. When I say high temperature, I mean really high, something like 2,000 degrees centigrade, which would be about 3,600 degrees on the Fahrenheit scale. This graphic here shows the type of structure that's formed as a result of that, and we'll be coming back to this in a minute to look at this in more detail. In the picture are spools of carbon fiber tow. Tow is a bundle of many individual fibers, and one tow could have thousands or tens of thousands of individual fibers. The manufacturing of carbon fiber involves trade-offs and achieving a balance between tensile strength and elastic modulus. If the elastic modulus is too high, the strength will be low and the fiber will be brittle. If the elastic modulus is too low, the material will be strong, but it will be way too flexy. This is the point made by Paul Liu of Reynolds Cycling, who says, as a general rule, as the modulus increases, the strength decreases and the fiber is more brittle. The grades of modulus that are associated with best practices for bicycle wheel production are standard and intermediate. Here's some information on fibers all the way from low modulus to ultra-high modulus. MSI stands for millions of pounds per square inch. It turns out that standard and intermediate work the best in bicycle rims. If I convert that into pascals, 1 pound per square inch is 6.9 times 10 to the third pascals. So a typical modulus of 34 million pounds per square inch would translate into 235 gigapascals. Let's illustrate what happens to the fiber. So we're going to envision a table, and I've marked off a square 1 meter by 1 meter, and I run along like that one length of fiber, and then next to it another length of fiber. I continue putting down my strands of fiber, spaced equally until I fill up my square. Now I'm very carefully going to flow onto those fibers a resin. So I now have a layer or a ply of reinforced carbon fiber, and this is called a prepreg because it is pre-impregnated with the resin. whereas my fiber itself had a modulus of elasticity of 235 gigapascals for the standard modulus. The prepreg sheet has a modulus of maybe 70 gigapascals. That's just a nominal number, and it's going to vary from one manufacturer to another. This is a roll of prepreg, which can be cut and shaped into patterns, much like you might cut and shape material purchased at a fabric store. This material here and this code is offered by Paul Liu of Reynolds Cycling as an example of the way that carbon fiber prepreg sheets and rims are coated, and we can get some information from some of the material in that listing of data. This bit of data here tells us that for a given ply, the mass is 120 grams per square meter, and it has a thickness of 0.0035 inches, which is 0.09 millimeters. So 0.09 millimeters is the thickness of one ply of the prepreg. If I calculate the density, I get 1.3 grams per cubic centimeter. This line here is telling me the percent of resin in the prepreg, so approximately 1/3 of the mass of the prepreg is due to the resin, and the other 2/3 being the carbon fiber filaments themselves. From the graphic, it's obvious that the rim is thicker in some places than in others, and that would mean that there are more layers of ply that have been laid up onto the rim in those areas. Where the side wall of the rim is, it's thinner. I may have only as many as 3 or so plies, maybe 3 to 6. Down here where the spoke bed or the nipple bed is, I may have as many as 70. And up here where the clincher part of the rim is, something in between that. This is the rear wheel from an Envy Smart 6.7 clincher set. The rear rim is 70 millimeters deep. The front would be 60. I want to show you a close-up of the cross-section of this 70 millimeter rim. So here it is, pretty beautiful rim. I'm going to show it to you from different angles. Very beautifully made carbon fiber rim. This is a photo I took with my camera of the cross-section of the rim. Down here, the rim is 2.2 millimeters thick, 0.66 at this point on the side, 0.65 here, 0.53 here, 2.4 millimeters here, and 1.7 here. If the 1.7 looks like it's more than that, it's because of my camera angle. This is obviously a clincher rim, and this part of the rim here has to be pretty sturdy because when I put a tire on and then inflate it, there is quite a bit of sideward force on the rim. If we expand that part of the rim, we see this picture here, and that side force from the air pressure creates a turning moment and tries to bend the rim out. That, of course, is not unique to carbon. Aluminum rims tend to do the same thing. This is known as UD prepreg, unidirectional. All the fibers are in the same direction. Now, as other layers of unidirectional prepreg are laid on top of this, they can be laid in the same direction as that layer or at any angle up to 90 degrees. This, on the other hand, is woven prepreg because the carbon fibers are woven together before the resin is applied. The layup of the carbon fiber rim involves applying multiple layers or plies, and there is a lot of opportunity to vary the direction of the carbon fibers to yield a particular desired characteristic. This results in a rim that has an anisotropic elastic modulus, that is, it is not the same in all directions. But this process gives engineers complete control over things like the structure, the strength, and mechanical properties of the rim, and it allows for a perfect reduction of the drag coefficient and ideal behavior in crosswinds. Let's compare these two wheels from Envy, the SES 3.4 on the left and the SES 3.4 disc on the right. The SES 3.4 has 20 spokes and it's radial lacing. The one on the right, 24 spokes, tangential lacing. We might reasonably assume that the cross-section of those two rims is the same. But they are not. If we look at the rim brake wheel on the left, we see that right here, the rim is thickened slightly where the brake track is. The rim on the right, made specifically for disc brakes, right here at the spoke bed is thickened because of the large braking forces. Critically important, the rims are not interchangeable. This rim here is made only for disc brakes, this one only for rim brakes. We've seen how carbon fiber and polymer resin can be combined to form a carbon fiber reinforced polymer. A very good analogy is how we can take rebar and concrete and combine those to form rebar reinforced concrete. We saw how we can take polyacrylonitrile and through a process of carbonization and graphitization, create this structure here. Now we can make three observations about the structure that was created. One is that most of the nitrogen and hydrogen has been driven off by the large amount of heat. Also, there's quite a bit of cyclization that has formed, and there is a lot of conjugation, which I will now explain. Conjugation involves alternating single and double bonds, and we see that in many directions through this structure. For example, there is a single bond, a double bond, a single bond, a double bond, single bond, double bond, single bond, double bond, and single bond. At the top is a sheet of what's called graphene, which has this extensive structure of conjugated bonds. It's shaped like a chicken wire, and it can be bent around into different structures. On the left is a buckyball, in the middle is a nanotube, and on the right is graphite. Here's another picture. In the upper right-hand corner is graphite, which you can see is just a very large number of individual layers of graphene. The processes of carbonization and graphitization in the manufacture of the carbon fiber result in a large amount of graphite or graphite-like substance being part of the composition of the fiber. Let's delve briefly into some chemistry and look at some structures of carbon. This is the crystalline structure of one of the forms of carbon known as graphene. Notice that it's a 6 carbon ring, hexagonal, and all of these 6 atoms are lying in the same plane. Here we see a continuation of that 6 carbon structure spreading out in all directions. So this is a larger piece of graphene. If I take this and I fold it around and form a tube like this, then I have formed a nanotube. Graphite is just a very large number of parallel forms of graphene. So if I start stacking these forms on top of each other, forms of graphene, then I have graphite. Notice that the bonds between the carbon atoms in each of these sheets is very strong, but the bonds between the sheets is very weak. So layers of graphene can slide easily past each other, which is what causes graphite to be rather slippery and is sometimes used as a lubricant. Now, carbon typically makes 4 bonds. Here you only see 3 to any carbon atom. There is a free electron for each carbon atom that spends part of its time above the plane of the graphene and part of its time below the plane of the graphene, and that makes these electrons what we call delocalized and free and movable. And that is what gives graphene and therefore graphite a special property. Here's a simple device for determining electrical connectivity, so I have a battery and a light and two wires. If I connect the wires, the light comes on showing that I have completed the circuit. Here's a graphite pencil. Because of the free electrons in graphite, it conducts electricity like a metal, as we can see here. Here's an NV carbon rim, and if I take my connectivity tester, connect it at one point and over here another, you see that my carbon fiber rim conducts electricity because of the graphite in it. You may not have found that interesting, but I thought it was, so I wanted to show that to you. The business of manufacturing carbon composites is a very big market and probably will become much larger in the future. There is understandably stiff competition between high-end manufacturers, and there's also a very rapid pace of research and development. So there are some very tightly guarded trade secrets, for example, about the specifics of the carbon fiber, the specifics of the resin, and the specifics about the layup and ply orientation.